I did. I guess I read
You go to
I don't want to have these person that's cursing. It's the person that's really talking thing. It might be international. They're not expensive. But if you even try to reduce it,
it's like
that's all it's a bit of I don't know any.
Yeah, it's like black. It's probably.
Okay, let's get started. Okay. All right, let's get started with today's lecture. Oh, brief announcement. We posted a rather long assignment on Friday, I think, which is a tutorial on the block sphere after the pretest, right? I think you must have seen that. I've extended the deadline for it because I just saw that it's a bit too long for me. So you'll have till like I think next Wednesday or Thursday to finish it. Okay, so today we'll conclude our discussion on the quantum circuits, and then we'll see how well it works. I created a little game to play with the quantum circuits that we'll try out today, and then we'll have a more math-based discussion because we need to learn the math of quantum computing, which is linear algebra, and hopefully we'll get somewhere into this list of topics by the end of today's class, and definitely by the end of the week. Okay, this is from last week. We had several gates that we introduced. This was the phase gate, which is a square root of the Z gate, corresponds to a 90-degree rotation around the x-axis, the z-axis, sorry, in the block sphere. And then we had the T gate, which is the square root of S, and that corresponds to, therefore, a 45-degree rotation. We went through all this last class. Then we introduced probably the most commonly used single qubit gate in quantum computing, which is the Hadamard gate, and just denoted by H. And this is a 180-degree rotation, but around an axis that's tilted. equidistant between X and Z in the block sphere. And some of the properties of the Hadamard are summarized here. We went through them in detail in the last lecture as well. So at the very end, I talked about this, which is that, and I introduced that web-based tool that you can use to like sort of chain together various quantum gates. We did, I just said, I just showed it on that tool, which is that you can just put together any number of blocks. It has various other gates in there, and we'll come back to them eventually. And the circuit, as we saw, is just read from left through right. And at the end, if you get this symbol, it means a measurement is made, or sometimes the symbol is left out, the meter symbol, which also implicitly means that a measurement is made. So before we go on, I thought it is good to illustrate one of these calculations by hand to show you that we do indeed know how to now manipulate or to understand what happens to a qubit as it goes through all these gates. So H T S H, and the initial state is 0. So we start with the 0 state, and we operate with it on it with the Hadamard gate. So sometimes I'll just show that to indicate that's the operation. So that results in the state H acting on 0, which is equal to the plus state, which is 1 over root 2, 0 plus 1. And then we can now operate on this state with the T gate. And notice how I'll write this state over here, which is T now acting on this state. So that's TH0. So you can see as I'm building from left to right on this circuit over here, the operation appears in the inverse order on the ket, right? So the ket 0 first is operated with H, then with T, and then with S and H again. So it'll look like the same thing, but just reversed, right? So just pay attention. I mean, just remember that, because we'll use it at other times. And this one, the T gate, is just e to the I pi over 4 acting on 1. So because gates are linear, let me back this up. Basically, T acting on each of these states over here. So it's 1 over root 2, T acting on 0, plus T acting on 1. The throat is still a little scratchy. Good. And that is just e to the I pi over 4. And just make sure. Oops. Interchange the T and S gates. No, that's right. Okay. Then we operate now with the S gate on this state that is equal to SEH acting on the 0 state. So that's again equal to S acting on the 0 state, S acting on the 1 state. So 1 over root 2 times S acting on 0 is 0. And on the 1 state gives me a e to the I pi over 2 rotation. And then that already has a E I pi over 4 rotation. That gives me this state, which I can write over here is 1 over root 2, 0 plus e to the I pi over 2. I could write it either as I, right? Because that's what e to the I pi over 2 is. But for now, I'll just keep it as e to the I, which is e to the I pi over 2 plus pi over 4 is 3 pi over 4. There, that gives me this state over here. Then finally, we need to act with the Hadamard operator or gate. So again, a Hadamard gate, and that acting on this state, which is so I end up with H, S, A, T, H acting on 0. That's our result at this point over here. That is the state H, S, T, H, 0 is what is coming out of this last gate over here. Okay. So I had to operate with H on this state over here. Now H acting on the 0 state, so H acting on the 0 state gives me the plus state. And H acting on the 1 state gives me the minus state. Okay, and so this is just collecting together all the terms. So I see 0 has e to the I 3 pi over 4 over here and 1 over here. So I'm just going to, and the 1 over root 2 times 1 over root 2 is common on both. So I just pull out the 1/2 outside. And so in front of 0, I have 1 plus e times I 3 pi 4 on the state 0 in front of the state 0. And then for the minus, for the 1 state, I'm going to get 1 minus e to the I 3 pi over 4, the state 1. Okay. Now you can visualize this on the block sphere. I'll show it to you on the PowerPoint, the next slide, but using the same techniques that we've already discussed before. You can like calculate what the XYZ coordinates are by converting this to a common form, remember? So if you get given any general state psi, you write it as some A times 0 plus B times e to the I phi times 1. So we have to express this state in that form, and then we can immediately associate A with cosine theta over 2 and B with sine theta over 2, and that gives us the thetas. But okay, so I'm skipping all those steps. You can write a little computer code, Python code, for example, is what I do, just to like calculate that automatically. And then we can then calculate theta and phi and then get the position on the block sphere. Okay. I'll show that to you on the next slide. But for now, our only concern is, remember at the end, we made a measurement, right? So we want to know what is the probability to be in the state 0. And that is just the component in front of 0. We want to take the modulo norm square of that. So that is 1 over 4, because remember there's a half sitting outside. So I take the square of that. And then 1 plus e to the I 3 pi 4 whole square. Now I can write that as 1 over 4 times 1 plus e to the I 3 pi over 4 times 1 plus e to the minus I 3 pi over 4. Right, that's what norm squared is. I take the number times its complex conjugate. So that's 1 over 4. And now I just expand out all of this 1, 1, And then this times that is e to the I 3 pi over 4, e to the minus 3 pi over 4. That also gives me 1. So that's e to the 0. And then I'm left with two terms, e to the I 3 pi over 4 plus e minus I 3 pi. So that is just identity, because we know that a number plus its complex conjugate, right, is divided by 2 is the real part of that number. Okay. That's exactly what we have here. So that is 2 times the real part of e to the I 3 pi over 4. So that's 2 plus 2. Real part of e to the I theta is cosine theta. So that's cosine 3 pi 4. So that's our final result. You can plug that in, or there's a small simplification you can make, because cosine 3 pi over 4 is cosine pi over 2 plus pi over 4, which is minus sine pi over 4. Anyway, whichever way you want to do it, you can plug that in and you get 1 minus 1 over. Any questions about this? This is just to show you, yes, you can indeed manually work this out. But of course, it was already kind of tedious, especially if you have large circuits with lots of gates. And we will now introduce in a few slides the tools for doing this much more simplistically, and using just, you can start writing code so that you don't even have to do it manually like this anymore. But let me know if you have any questions. Because I find a lot of times for small circuits, it's easy enough to do this and quickly make sure that I've done everything right, rather than firing up some linear algebra package. Okay. So here, yes.
If we switch the S and T8s like the order,
Yeah. In this case, they don't, because they're both rotations around the z-axis. So you can see if I rotate by t, which is a rotation around the z-axis by pi over 4, and then rotate with s, that's another rotation of pi over 2. If I interchange those orders, since they're around the same axis, it doesn't matter. They can be interchanged. And this is a good question, because we will see there are situations where we can't quite do that. Okay. There are exercises that we'll assign to you that will illustrate some of that. So this is that state that I just derived on the chalkboard. This is its block sphere representation. And you can see it's down towards the southern hemisphere of the block sphere. And that will make sense, because when you calculate the probability to be in the 0 state from that calculation I just did, you'll see it's less than the probability to be in the 1 state. Makes sense, it's closer to the South Pole than to the North Pole. Okay, so I wanted to, before we get into the math of linear algebra, try to illustrate that even with the small number of simple gates that we have found, we can prove. When I say prove, I mean, I'm not talking about like a mathematical proof, but I can already show you that there is more power with these simple single qubit gates that we have now introduced than you previously had with just Turing machines. So I was trying to come up with an illustration or an example of how to show that, and I've come up with this game. So I'll lead you through the game, and hopefully this is the first time I'm trying it out. So, feel free to interject and say that something wasn't clear or something wasn't, didn't make sense. Hopefully by the end of this, I'll convince you that we have sort of understood some intuition for why the quantum circuits are more powerful than Turing machines, even with these single qubit, simplest gates that we can make so far. Okay. So bear with me as I try out this exercise or this game. I called it the imitation game, of course, in honor of the movie. Okay, so we introduce our favorite quantum computing skeptic, Alan. Okay, and Alan is a strong believer in the strong church-Turing thesis, and he says all this quantum circuit stuff is just nonsense. These quantum gates. You're just making up some fancy words. I can imitate all this with a Turing machine and a coin. So what I mean by that is, Alan says, if you allow me probabilistic Turing machines, I can simulate all this stuff that you're doing. Okay. So in the example I'm going to show you is like a toy example. I'm not proving every single thing here, but hopefully we can play this game and see. And the only condition is that the input states that he wants to see, he says all this fancy, like your superposition stuff. I don't believe in all that. Anyway, in the end, you're observing stuff only in 0 or 1 basis. So your inputs must be 0 or 1, your outputs must be 0 or 1. Or blanks. Okay, you can say that there can be blanks. Okay, that there are sometimes, you send in a tape cell that's just a blank, and that's okay. Okay. Is the game rules sort of clear? Yes? Okay. So Alan says that everything that you do with quantum computing, I'll be able to come up with a good imitation of that with these machines and these rules. And Kadir, our heroine, is like, yes, I'm ready. Let's bring it on. Okay. So Alan first constructs his plus Z Turing machine, and the plus Z Turing machine takes in zeros and puts out zeros. Okay, very simple Turing machine. Okay, and if you send in a 1 into this Turing machine, which is a minus Z state, he puts out blanks. Okay, so he blocks the minus Z machine. So effectively, he blocks minus Z states. Okay, so he builds this. Okay, everything I just said is just in these words here. Okay. He also builds the minus Z Turing machines, which do exactly the same as the plus Z Turing machine, except with minus Z input states. So if you send in a 1, then it puts out a 1 and blanks if you send in anything else. Okay. So if you send in a 0, it will put a blank. If you send a blank, it will put out a blank. Okay. All right. And he builds one more machine, which is the plus X Turing machine. Okay. And so the plus X Turing machine, what it does is it flips a coin. So if Alan sends in a plus Z into the Turing machine, the output will be either 0 or 1. I've drawn it as 2 arrows, but please understand that this is just one output. Okay, there's just one output coming out. But it's sometimes a 0 or sometimes a 1. Okay? So it can be sometimes 0, sometimes 1, which is decided inside the Turing machine by the flip of a coin. Okay? And the same will happen if you send in a 1 state. Okay? Be sometimes a 0, sometimes a 1, and blanks, of course. Yeah. Okay. So he thinks that with these, he can already, and okay, if you wanted to do a T gate or whatever, you could like simulate this by a biased coin. But for our example, we're just choosing a perfectly balanced coin. So it's always half-half in this case. Because, I claim to you that with a Hadamard gate, which is the most important gate in quantum computing, that's his aim. He's going to show you that you don't need all this fancy stuff. Okay, and that is just what I said over here in words. Yeah. Okay. So now let's look at what happens as you chain these machines together. Okay. All right. Let's take the plus Z Turing machine. We send in a 0 state. Well, you get a 0 state out, right? And if you send it to another Turing machine, again, you get out a 0 state. Okay. Easy enough. So you always get a 0 at the end of this operation. And if you send a minus Z Turing machine, you send a minus Z state or 1 state into a minus Z Turing machine, and you chain it to another minus Z Turing machine, it sends you back the 1 at the output. So Turing machines of the same type, when they're chained together like this, they just keep producing the input state. Because if I send in a 0 to the minus Z, it gets blocked out here by a blank, right? And then the output will be a blank, which is also okay. Oops. Oh, I just illustrated that. Oh, and if I send a 0 into a plus Z Turing machine, I get a 0. And then if I send that to a minus Z Turing machine, I get nothing, right? So, my probability effectively of observing a 1, if I send in a 0 into a plus Z and a minus Z Turing machine, is 0. Okay. Okay, so far on this? Okay. And of course, if I interchanged the minus Z with the plus Z and I sent in a 1 state, then everything would be the same if you still get a blank. Okay. So the plus Z and minus Z act like sort of blocks or filters of these states, 1 and 0. Okay. Oops. Animation is a little bit off, but okay. And now we introduce the unique machine that he has built, this plus X Turing machine. So what happens if he takes a 0 state and feeds it to a plus Z Turing machine? He's going to get out a 0, right? And then he sends it to a plus X Turing machine, and what do you get on the output? Yes. Sorry, can you speak?
50%.
Yeah, 50%, one or the other, 0 or 1. Okay. 0 or 1 with 50% probability. All right, Alan is feeling increasingly happy. He's like, see, I can reproduce what you do with your Hadamard gates and all that stuff with my plus Z and X Turing machines. I'm able to just produce the same kinds of output probabilities that you can, right? If I, in our quantum gates, if I had sent in a 0 with a Hadamard or a plus X or plus Y, I would end up with 50% probability to be in the 0 or 1 state. So most of the stuff is, oops, sorry about that. Well, let's make sure that when we chain plus X to plus X, what do we get? Okay, let's also make sure of that. Okay, because so far we've been chaining Z to X and so on. Let's also chain X to X. Okay, so send in a plus Z to a plus Z Turing machine. Well, I could omit the plus Z Turing machine. I could just send Z, but okay. I always put that plus Z to sort of purify the state, so to speak. Like make sure that the output is always a 0. Okay, all right. So output is always a 0, and then I put a plus X Turing machine, and then I put another plus X Turing machine. What will the outputs be over here? Yes.
50%, 0 or 1.
Yeah, 50%, 0 or 1. Does everybody agree? Half the time there's zeros, and then that will give you a quarter of the time 0 and 1, but then there's another half of the time it's 1, and sometimes those ones become zeros and ones with half and half probability. So all in all, it maintains the statistics. So plus X and plus X together keep producing back with me the same statistics so that's good, right? It kind of consistently gives me the same statistics, no matter how many of these I would chain together. So Alan is like, okay, I've done it. Nothing to this quantum computing nonsense. Everything that you do with all this probability stuff and gates and all this stuff, I can do this with my Turing machines. And then, Kadira is happy. She's like, yes, now I'm going to show you something, right, that you can't do with your probabilistic Turing machines. Okay, so Kadira comes in and she brings in a special box. Oh, sorry, do you have your hand raised? Oh, okay. Any other questions so far on this game? Okay. Now she gives Kadira gives Alan two special boxes labeled QH. Okay, Kadira's had them on her. All right, that's our, we know what's inside. But she tells Alan, don't look inside these boxes. Okay. And don't look at the output of the boxes here. I should have mentioned that, but don't look at the outputs. Okay. All right. And she says, okay, put your QH in front of your or after your plus Z Turing machine. Alan feeds plus Z into this QH, that is a zero state, and measures the output, and he gets half and half probability, 0 and 1. He's like, well, that's what my plus X Turing machine does. This must be just a plus X Turing machine sitting inside this QH box. What's so fancy about your QH? Okay, it's just another word for my plus X Turing machine. But now, and what do you think will happen if he changes the output of the QH to a plus X Turing machine? Yes? Exactly. So he puts his, to check that what Kadira has done is just a fancy version of his plus X Turing machine. He puts another plus X Turing machine in front of this box, the QH. I mean, he can, I should mention he does a lot of other checks, right? I mean, to be careful experimentalist, you know, he looks at these and puts plus Z Turing machines here and minus Z Turing machines and makes sure these outputs are really just Z and plus Z and minus Z and all that. He's a good experimentalist, okay? So he makes sure that it's really just zeros and ones coming out of here, not something weird, okay? And then after that, when he does this test, he puts his X Turing machine, which he has already previously verified. Remember, when we earlier did the plus X and plus X version a couple slides ago, remember? When we had just plus X and plus X, we ended up with 50-50 probabilities again on the output. So by checking with his plus X Turing machine here, he is now convinced that what's coming out of Kadira's machine is just another kind of X Turing machine, plus X Turing machine. Okay? Because as he said, when you put that plus X Turing machine, he gets 50-50 probabilities for the output. Is everybody okay with that? What do you think happens when he now takes Kadira's QH? Remember, she gave him two boxes, right? QH. He changed the output of the QH to another QH. What do you think he gets at the output? If you send it a 0. Yes? A plus state. But remember, in our rules, we are always only allowed to measure zeros or ones. So you're saying half and half?
Yeah.
He would get zeros and ones? Okay, so that's one possible answer. That would look just like this example, right? Because when he did this, he also got zeros and ones with half and half probability. QH and QH is H and H together, right? What does our quantum circuit knowledge tell us will happen when you put two H's together? Yes. Back there. I'm sorry, I don't know your name. What's your name again? Huh?
Me?
Yeah.
Anish.
Anish, yes, Anish.
Is it just like a full rotation we get started with?
So that would be?
I guess it's 0.
Yes, exactly. Aha. He gets zeros with 100% probability. Because another fancy way of saying that is H squared is the identity matrix, identity operator, which was one of the definitions of H. It's also because, as you remember, in the block sphere, H is rotation around the x plus z axis by 180. So if I rotate again, I come back, as he just said, back to the starting point. So very big difference from the plus X Turing machine that we verified will never give us that. It will always give us half and half. Alan is very unhappy. Okay. He's like, what? There's no way this should be happening. We have just seen the first sort of example of how a quantum circuit can do something that probabilistic Turing machines cannot. Okay. Tell me if this example or this game helped you a little bit, because as I said, this is the first time I'm trying it. Okay. So my conclusion from this, because I know it's a bit grand conclusion, we haven't mathematically proven anything here. Okay. The mathematics of it is, I would have to take much more generalized Turing machines and all this stuff and be much more, rigorous and all that. I was just trying to give you an intuition that already with these simple circuits, we can show results that cannot be simulated with a probabilistic Turing machine that violate the strong Church-Turing thesis. Okay. The reason, of course, is, again, it's our old friend superposition, right? Because if Alan were to measure what was happening at the output of the QH box, I didn't go through that case. So suppose Alan gets upset and looks at the output coming out of the QH box. Basically, he's measuring whether the qubit is in the 0 or the 1 state, right? Then what do you think he gets at the output here? Yes.
50-50.
50-50. Exactly. So it's back to our old friend, the watching pot never boils or whatever, the watched particle collapses into a wave function and then returns back to being a classical object. As long as you don't observe it, though, if you keep going through this quantum circuit, it can exhibit behavior, which is a constructive interference or destructive interference. In this case, constructive, it reproduced back our original state 0, rather than flipping it to the 1 state. We could also make it flip to the 1 state if we want. So Karina can build a special box. It's just QH with another gate in it. The next gate, for example, which would always produce now the flipping from 0 to 1 with 100% probability. So with these examples, I try to illustrate for you that even though these Hadamard and other gates, they look, kind of complicated, they have some real results, real, usefulness by allowing us to build a circuit that we couldn't have built with just probabilistic Turing machines. That is, by building a machine where we compute something and flip a coin, that's not enough to just simply produce some probabilities similar to, say, the Hadamard gates or the other gates, of course, e to the I, the T and S and so on. Okay. So that's our imitation game, and we have failed at imitating quantum circuits. Okay. Pause here. Any other types of questions, remarks, comments? Yes.
So we saw that quantum computers cannot be solved by using probability. What about the
Okay, so your question is, can probabilistic Turing machines be modeled by quantum computers? I think the belief is yes, that BQP, the class of problems that can be solved by quantum computers, is bigger than P. And therefore encapsulates P, so to speak. Yeah. We don't think there are problems in P that are not, that are not solvable by BQP. That at least is our belief. I mean, we have some examples of problems. The problem, of course, is we don't know which problems are in P or NP, right? And we are still, the jury is out on things like that, right? Is that because we have a class of problems in NP, we don't even know. Maybe they are in P actually, right? So that problem is still to be solved. Okay, so any other questions? Okay, if not, we will now introduce a tool that will make our calculations like, like the calculation I showed for you of a quantum circuit. And these kinds of quantum circuits, we want to have tools that will allow us to make these calculations a bit simpler and easier to understand. Okay. And so we'll start with the logical basis states, 0 and 1. Okay. And we will write them now as column vectors of numbers. Okay. So instead of just writing the ket 0, we will write it as a column vector like this with two numbers in it. Now, these two numbers can be in general complex, but for the basis states 0 and 1, they will just be this column vector 1, 0 for the state 0 and 0, 1 for the state 1. Okay. So these are column vectors. Some of you may be familiar with like linear algebra, then you know that these are just vectors in a linear vector space, basically. But the point is, and of course, as I said, the operations on these column vectors are linear. So I can add 0 plus 1, and I'll get the state 1, 1, right? Because I'll add 1 to this component of this 0 and 0 to this component of the 1, and I'll get the state 1, 1. Okay. And other linear operations that I could do, maybe I'll sketch it on the next when I go to the blackboard, is I could multiply 0 by a, some number, complex number in general, then I'll get the state a times a on the top element and 0 on the bottom element. So that's just a multiplying throughout the column vector, each element of the column vector. And then say I multiply this by b, and then that'll be b times 0 on the top and b times 1 on the bottom. So that'll be 0 b, right? And then I could add those two together. So a times 0 plus b times 1, right? A times the state 0 plus b times the state 1 will be the column vector AB. Does that make sense to everyone? Sorry, I said it in words. I should have just written it out, but. Not hearing any questions, but feel free to stop me at any time. So what about the generic qubit state? Well, that's just the state side. Okay. So write it on the board now. What I just said in words, you can write out explicitly. Any general qubit state, we know can be written as A, where A is a complex number, and plus B times 1, right? This is the most general qubit state, which in the linear algebra language is A times the column vector 1, 0 plus B times the column vector 0, 1. And as I said, A multiplies each element in the column vector. And B similarly multiplies each element in the column vector and gives me this state, AB, for the state side. We call our states as kets, right? These are kets or basis kets. So the basis kets are basically being represented by these 1, 0s. So we could also take some other basis state plus, which as we know is 1 over root 2, ket 0 plus ket 1, which again I already did the most general case, so it should be no surprise. This is just the state 1 over root 2, 1, 1, right? So those are just two very simple examples for qubit states and how they correspond to column vectors. Yeah, I wrote those out on the board. And now we introduce one more quantity, which is called the dual of the column vector. Okay, so with every column vector, we associate its dual, which is the complex conjugate transpose. Okay, and the definition of the complex conjugate transpose operation, I'll show you in a minute. But the notation for it is we take whatever column vector it is and we put a dagger on top of it. Okay, so superscript with a dagger. That's to denote the operation of complex conjugate transpose. And this vector, this dual vector, is called the bra vector. Okay, and the reason is as we put them together, the two will be the bra and ket, bracket. Okay, that's where that two words came from. When Dirac was writing this, it is usually this complex conjugate transpose with the dagger. Instead of writing it that way, we write it this way. That is with the left angle bracket and the same state psi, and then 1. Okay. So if the state psi, which is AB, right, column vector, then the operation of taking complex conjugate transpose will give me a row vector. Okay. So the bra vector, which is this dual of the column vector, associated with every column vector, I can associate a row vector, which is this vector over here, the bra, which is A star, B star, written in a row vector form. Okay. Now, I understand that the bra vector is always a bit confusing because, it's like, okay, where did that come from? We don't know what it's good for. And so one of the things that, and of course I should mention, they're equivalent. So corresponding to the dual of the bra vector, which is, I would take the complex conjugate transpose of the row vector, I would get back the column. Yeah, you can verify for yourself that doing that, if you know a little linear algebra or matrices, then this will make sense to you. But you don't have to know it, you can just accept it. This is true. Okay. So the way I think about the dual vector, it's actually not a vector, okay, in some sense. It's not a vector in the sense we think of kets. So kets are column vectors, they are our physical states. Remember, like when we talked about a qubit state, we talked about qubit state like a photon or a spin of a particle. You've already seen what the physical qubit state look like. We read that paper, we saw that you've been assigned and all that. So we know that physical qubits, and now we have mapped them to these, kets, and then we have mapped them further to these column vectors. So the column vectors or the ket states, these are the sort of the physical states that we are worried about, like that we care about. Okay? The dual you should think of as simply a function. Okay, it takes a column vector and maps it to a real number. Okay. A real number that we can measure. Okay? And that is really what the dual vector is there for. Okay. Yeah, this just states what I just said over here. And so yeah, all that, these two statements. So just think always of the dual vectors. I always think of the dual vector, the bra vector, as being hungry. They're always hungry. They're always looking for a column vector to attack. And if they can find a column vector that they can attack and operate on and give a real number, then they're happy. Okay. So they are always like a function. Okay. You can think of them like a function which always needs an argument, something to fulfill its purpose and spit out a real number that we can then observe in the lab. Okay. Okay, so let's take the dual of a few different column vectors just to make sure we have it absolutely embedded in our mind on how to take the dual. . 。 So let's take, of course, our usual basis states. So 0 is the column vector 1, 0. Its dual, which is the state, the dual, which is the bra vector 0, would be simply complex conjugate transpose the row vector 1, 0, right? Because I take the transpose, which is flipping it over on its side, basically, going from being a column to being a row, and then taking complex conjugate of each of the elements. Since 1 is a real number and so is 0, that's just 1, 0 on its side. Same with the state 1. Taking the dual, is the bra vector 1, which is just 0, 1. And we just did the state plus, which is just 1 over root 2, 1, 1. We can now find its dual, the bra plus, which will just be 1 over root 2 times the row vector 1, 1. And again, bra vectors are also linear. So when I pull the 1 over root 2 outside or inside, it doesn't matter. Okay. What about minus? Okay, I won't do the minus, it's just the same. But let's do one which is plus I. Okay, remember the plus I or the y-axis state, right? So that is the state 1 over root 2, 1 I, right? And now when I take its dual to give me the dual, the bra vector plus I, that is 1 over root 2, 1 minus I. Because I have to take the complex conjugate of I, that gives me minus I. Okay, and the most general state psi equals AB. Well, I've already told you by the very definition that its dual, the bra psi, is just A star B star. Okay, we already said that in the definition, but reiterate, following the same pattern as these other vectors that we've just seen. Any questions? Okay, so we've introduced two types of vectors. Column vector corresponding to the kets, and the row vectors or the dual vectors, the bra vectors, that correspond to these type of states, these row vectors. Okay. Did I miss anything in the previous slide? Yeah, we did all those examples. Very good. So now we want to introduce the famous inner or dot product, which is, as I said, that's where the name, the bra and the ket vectors came from, representing the bracket. Good. So let's say we have two states. So first state is the state psi, okay, which is the column vector AB, and phi, which is the column vector CD. Okay. And we're assuming these are qubit states, so everything is normalized and all that good stuff. Okay. And the inner product, or I'll call it the dot product, okay, is defined as phi psi. So bra phi acting on ket psi. Remember, I told you that these bra vectors are hungry for something to operate on. So the bra phi will operate on the ket psi through this mathematical operation. Okay. And we will now see that this is indeed going to give me a number. Okay. So this is the row vector. We just saw that the row vector corresponding to that phi is C star D star. And now I'll multiply it with this column vector A, B in this way, which is, I should have maybe written that out in an equation, but it's good to illustrate this. B star, B star, operating on the column vector A, B, gives me the number C star A plus D star B. That is, I take the first element and multiply by the first element, take the second element, multiply by the second element, and then add them together. Okay. Now we can also define, of course, the dot product of phi and psi. We can take the other way, which is the dot product of psi with phi. Okay. So let's look at that as well. So this was the dot product phi psi, right? That's what I just defined for you. I can also look at the dot product psi phi. Okay. And by the same definition, I must now take the row vector A star B star, multiply it by C D, right? And that will give me A star C plus B star D. If I compare these two expressions, okay, I'll see that the first term over here is the complex conjugate of this term. Because if I take complex conjugate of A star C, that's complex conjugate of A star is A, complex conjugate of C is C star. So that's the same, and these are just numbers, so it doesn't matter which way I write them. So that's just C times A star. Okay. So complex conjugate of A star C is C star A, complex conjugate of B star D is D star B. Therefore, we have arrived at an identity which is that phi psi is always equal to the complex conjugate of psi phi. Okay. This is good because, for example, if I look at the complex conjugate or the dot product of a number of a state with itself, phi phi, right? By this identity, that must be equal to interchanging phi and phi, complex conjugate of itself, but a number that's the complex conjugate of itself must always be real. So what it states is that the dual vector of a state acting on itself, on its ket vector, must always give me a real number. So this is the start of understanding that these dot products, right, return real numbers when they act on each other, on themselves, for example, right? The bra vector acting on itself, on its dual, must always give me a real number. So the most general case is not necessarily real, but that's okay. We haven't yet put any significance to a bra vector that acts on another ket vector. Okay. All right, now any questions so far about the dot product? So you can start to think about the dot product as taking a projection. Remember in like real, when you learned about vectors in the beginning, right? You have some vector A and you have some vector B. Then the component of vector A along B is A dot B, right? So which I can take by just projecting onto this axis here. This number is A dot B, right? You remember this from vectors, maybe? So in the same way, we're going to see these inner products are representing a projection or an overlap of one vector, state vector psi onto another state vector phi, for example. That's sort of the physical sort of visualization, if you like. Of course, this is occurring not in a real vector space, but in this linear vector space composed of complex numbers, basically, the Hilbert space, of qubits. The two-dimensional complex vector space for qubits. It gives us a way to sort of associate some kind of idea of like how good or how much of one state is similar to another state. That's what this dot product allows us to do. Yes. Yeah, that's just what I wrote earlier. Oh, so I did write it. Okay. At least I wrote that result down. Okay. And we just proved this property over here that phi psi equals psi phi star. Okay. So the next thing that we can show is that the inner products of states that are opposite to each other on the block sphere are always zero. Okay. All right. The drawing board. Once again, just by mechanically following our rules, this will come out to be immediately obvious. Okay. So the state 0, remember, the state is the column vector 1, 0. The state 1 is the column vector 0, 1. So the dot product between 0 and 1 is this state, right? It's this dot product over here, which is bra of 1 acting on 0. So that is just 0, 1 acting on 1, 0. So you see 0 multiplying 1 is 0, 1 multiplying 0 is 0. So the answer is 0. Okay, that was easy enough. Let's do a slightly more screen. Let's do a slightly more difficult one. State plus, which is 1 over root 2, 1, 1. State minus, which is 1 over root 2, 1 minus 1. Remember, we showed this by just looking at the definition of the states plus and minus. So again, I want to calculate the overlap or the dot product between minus and plus. I take 1 over root 2 of this guy, row vector, times 1 over root 2 of this column vector. Okay, that gives me 1/2. And now again, 1 times 1 is 1, and then minus 1, minus 1. Minus 1 times 1 is minus 1. So again, I get a 0. Okay, the last one, obviously, we want to verify is our basis states along the y-axis. Plus I 1 over 2, 1 I. Okay, this one we have to be a little bit more careful because there are imaginary numbers involved. So the bra minus I with the bra with the ket plus I is 1 over root 2. And now I take minus I and take its conjugate transpose, which is 1I, right? So this and this. That's this complex conjugate transpose of the state minus I. And I have to multiply it by the column vector 1 over root 2, 1I. Gives me again 1/2 times 1 is 1, plus I times I, which is minus 1. So again, so that is showing that all the basis states that we did, and you should verify for yourself that plus overlap. What is the overlap with like 1 or 0? You can do that. Those are other things you can verify. You will find they're not always 0, right? Because plus and 1 has some component, and we'll talk about that in a minute. Any question about this math here? And we can also show that the inner product of a valid cubic state with itself is always 1. So psi bra with ket psi is 1. Okay. Do I need to sketch the proof, or do you think you understand it? Anyone want me to sketch it out? I can. I don't mind. Don't be shy. You're not sure, speak up. Okay, all right. I'll let you do it as an exercise. It's fairly simple. Just same rules, follow the same rules. You'll get, the answer. So since we have just said that the inner product of a state with itself is always 1, as long as it's a valid, meaning normalized cubic state with itself is always 1. And we also showed that the basis states are always orthonormal to each other, meaning 0 and 1 are orthogonal to each other, sorry. But by orthogonal, you understand what I mean, which is that the overlap between them is 0, right? That the inner product of, say, 0 with 1 is 0, the inner product of plus with minus is 0, inner product of plus I with minus I is 0. We just saw that on the chalkboard. And now I said that the inner product of a state with itself is always 1. So we call these states orthonormal, meaning these basis states are orthogonal to each other. So plus with minus and 0 with 1 and plus I with minus I, and they're normalized to 1. That also makes sense from that, block sphere picture that, the points on the opposite sides of the block sphere. They look like they're 180 degrees apart, but there's a factor of half that we have talked about. But anyway, so they're like orthogonal in this complex vector space. Any other questions? So it's an orthonormal. This will be a word we might throw around. Sometimes it just means this, that you have basis states which are always orthogonal to each other and normalized to 1. And now this comes back to what I was just telling you, that we can always find the component of a qubit state along a basis state by taking the dot product of that qubit state with the basis state. Okay, just with that picture I drew for you here. There it is. I guess I understand. Anyway, we'll demonstrate it. So let's see. Do I have anything else written on this? No, I just wanted to show you. Okay, so yeah, actually let's do it. Take oh yeah, okay, I do. So let's bring it up. Sometimes I have time to write all the equations down on the slide. Sometimes I just do it on the board. So I can never remember. Damn, I guess I have to. Okay. All right. So I just went, this is the state psi equals AB, right, in our column vector language. And this is that same state written in our old ket vector language. Yes. Did you have a question? Oh, okay. And now I'm going to take the projection, the dot product of psi with the state with the bra 0. Okay. In our ket vector language, this would be written as bra 0 acting from the left onto our ket psi. So that if I take that bra 0 inside, it will give me 0, 0, the bracket 0, 0, and the bracket 0, 1 on this side. Well, we just said the bracket of 0 with itself is 1, right? Because it's normalized. The bracket of 0 with 1 is 0. Correct? Because we just said that they're orthogonal to each other. So the result must be the number A. Okay? And on this side, we can see the same thing in this language of the column and the row vectors. If we take the row vector 1, 0 and multiply it by the column vector AB, then that's 1 times A plus 0 times B. So the end result in the end is the number A. Okay. So this number A is the coefficient or the component of the ket vector psi along the state 0. Okay. And this dot product language makes that a little bit more geometrically nice because it reminds you of things that you have done with like regular vectors, where if you want to find the projection of some vector r onto the x-axis, you take r and you take its projection, meaning its dot product, with the x-axis. Or you want to take r and project it onto some other plane. For example, you take a vector in that plane and find its projection, its dot product with that vector in that plane. Yes?
So we see that psi is traditionally written in a kind of 0 state. Could you dot product with, like, for example, a plus state?
Oh, that is what I was going to get to next. So written in this way, it's not very interesting because you can read off the coefficients right here, right? I didn't need to know linear algebra or dot products really to find the component of psi on the 0 state. I just read it off here or read it off here. I say, oh yeah, A is up there, B is up there. Fine. B is down there. Okay. So I know what the numbers are. Why go through all this? The real interest is, as he just said, now what happens if I want to take the projection or the component of the state psi onto some other state? Like I was telling you, like when you first introduce vectors, you give them 3 numbers, x, y, z, and you say, okay, here's the vector. Okay, what interest is that, this dot product? At this point, I know the components of r along the x, y, z axis. The real interest is if I want to find the projection of r onto some plane that I don't know, or that's hard for me to find out. This is a mathematical way to simplify that operation. And I just repeated it now for B. Okay, just the same thing, but now with the bra vector 1 are acting from the left on the state side, and on the other side, I've shown you the same thing with the row vector for 1, which is 0, 1, acting on the state side. And that, with no surprise, gives me the state B, the number B. So, one last thing I want to point out is since each of these numbers, A and B, right? If I look over here, sorry, A is the projection of psi onto the state 0 or the number 0 psi, bracket 0 psi. Similarly, the number B is the bracket 1 psi. I can replace A and B by this general equation. That is, psi in terms of the basis state 0 and 1 is found by taking its projection psi onto the basis state 0 and the projection of the basis of psi onto the basis state 1. So find the projection of psi onto the basis state 1, multiply that by the basis state, find the projection of psi onto the basis state 0, multiply that by the state 0. And this now allows us to generalize to any basis state. Okay? As long as those basis states are orthonormal to each other, right, or an orthonormal basis state, we can replace the zeros and ones by those states and we'll get the same result, and we'll demonstrate that in a minute. Okay, but I'm out of time. So all I want to end with today is the probability to be in any of these basis states is then found by taking this coefficient and finding its norm square. Okay, so I'll end with that today. And next class, we'll demonstrate that last thing that he was talking about, which is to find it along any general basis.